this lecture series. This meeting is being recorded to continue. All right. So welcome to this lecture series on Deep Learning 101 for physicians and other busy people. My name is Sven Bambach. I'm a data scientist, and I'm really giving this lecture on behalf of the entire RISI NCH data science team. This is kind of part of our semi-official lecture series on AI in healthcare. You might have seen a lecture by my colleague Tyler Gorham, I think about 2 months ago, AI in Healthcare, Hype and Reality. And really what we're trying to do here is we're trying to have several related lectures that are all in some way about AI in healthcare, but they also all stand for themselves, so you don't have to worry about catching all of them. And this can really be anything from purely teaching about a specific topic, like I am teaching about deep learning today, or it can be something very practical, like one lecture we're planning, for instance, goes over all the steps that it takes to deploy a machine learning model here at NCH, for instance, deploying it as part of EPIC. And it really depends on what you would like to know. So if you have specific questions or specific things you would like to learn with regard to AI and machine learning, deep learning, whatever it might be here at NCH, let us know, send us an email, or you can also fill out the survey that you get after this lecture. All right, I think the agenda for today is quite ambitious, so I might take up the hour even without any questions, but I'm happy to adjust that, so don't feel discouraged from asking questions. You can just unmute yourself, or you can write it in the chat window. I can't directly see the chat when I'm presenting, but maybe some of my colleagues from the data science team can kind of moderate this and ask questions from the chat when there's a good time. All right. So with that, I had to define CME objectives for making this talk. So I thought these CME objectives can also function kind of as the table of content for what we're trying to cover here. So the first thing we're trying to cover is understand how deep learning relates to machine learning and AI, just have an understanding about where these terms come from. Once we've done that, we're going to try to acquire a very basic mathematical understanding of deep learning. And lastly, identify areas within medicine where deep learning can create values. So that's kind of, those are objectives, and that's kind of the table of contents roughly of this talk. So let's start with the first part, understanding how deep learning relates to machine learning and AI. It just shows roughly the idea that when we talk about artificial intelligence, we usually talk about what is called narrow artificial intelligence, which means having a computer solve a specific task in a human-like fashion. And really, machine learning is a subset of this idea of AI, and deep learning is a further subset of machine learning. So the reason I'm showing this figure here again is that I'll talk about this figure in more detail later, but I just want to make clear that in order to have an appreciation about what deep learning is and how we have to see it in context to machine learning and AI, I think the best idea is to start with machine learning and give you a little bit about a little bit of an idea about where this term comes from historically in the context of computer science as a research field. So I'm a computer scientist. That's where I've done my PhD. So my whole perspective on this is kind of based or flavored from a computer science point of view, but I hope this flavor or perspective can be useful to you as well. So let's start by going into the history of machine learning. So machine learning, the term machine learning was coined by a computer scientist, kind of one of the godfathers of AI, called Arthur Samuel in the late 50s. And he called machine learning the field of study that gives computers the ability to learn without explicitly being programmed to do so. And in order to understand why that's important, you have to think about how we're trying to think of the role of computers as we were kind of building the first computers. Traditionally, we thought of a computer in a kind of expert system approach, which means that the computer basically emulates an expert in some specific domain. So the way to think about this is that you supply data to the computer, and you supply a program to the computer, and then the computer gives you the desired output that you want based on the data and based on the program. To give you one example, let's assume your data is a spreadsheet with someone's credit history. And then the program is just a bunch of if-then rules that comes from some sort of human expert, like a banker in this example. And really the computer's role is just to run this program on the data and give you the output, like whether a credit has been granted or denied, right? But if you think about this, the computer is really just kind of emulating the expert, and all the expertise comes from a human as opposed to the computer itself, right? And this is in contrast to the machine learning approach. You can think of the machine learning approach by kind of shuffling these arrows around a little bit, where the input to the computer is the data and the desired output, and then a computer is supposed to produce the program that eventually creates the output that you're interested in. So one of the historically first examples where this kind of ideology came into place was with spam detection, right? So in order to classify an email as spam or not spam, it's not really feasible to have some expert that gives you a bunch of complex rules, right? That's not that easy to do. But what you can do is you can read a bunch of emails and mark them as being spam or not spam, and you can be reasonably certain about that, right? So you can provide the computer with a bunch of emails that are labeled as spam or not spam. And then what you want is for the computer to use these example emails to somehow come up with their own spam filter, right? That can then correctly classify emails as spam or non-spam on its own, right? So it's kind of a different approach where, as opposed to telling the computer what to do, we tell the computer, here's the data, figure out what to do, right? So this is kind of where machine learning comes from historically in a computer science sense. All right. So coming back to this diagram, I said that machine learning is a subset of artificial intelligence. Well, what else is artificial intelligence, if not just machine learning? What other problems can we think of? And I thought, to give a good idea, I went back to my textbook, my artificial intelligence textbook for my graduate level course. And I looked through problems that I had to learn about and picked out problems that had nothing to do with machine learning, but were still considered AI problems. So one thing you could think of, for instance, that people try to solve is search and planning problems. Those are very complex problems. If you think about your GPS, for example, your GPS needs to figure out the most efficient way to get from where you are right now to anywhere in the world where you want to be, subject to having the shortest route or the fastest route, whatever it might be, right? This is actually a classic AI problem where you have to efficiently search a space of options or plan a route, given millions or infinite possibilities, right? But it has nothing to do with machine learning. You don't need to use data or anything to do this task. Another example is solving games, moderately complex games like chess. You can actually use a very similar strategy here, where it essentially is also a planning problem. You have to kind of plan the best move or search for the best move in the face of having a lot of possible moves to come from. Again, classic AI problem in the computer science literature, but it has nothing to do with machine learning, at least traditionally. And even simple robotics problems is something that we would consider AI, but have nothing to do with machine learning. For instance, imagine you have a robotic arm that has a bunch of joints and degrees of freedom. You want to grab a certain space, a certain point in space. So you need to figure out how to move the robotic arm in order to reach that space. That's, again, a motion planning problem that you have to solve. It's considered AI, but it has nothing to do with machine learning. Now, machine learning, again, as a subset here, as we already talked about, deals with problems where we have to learn from data. And sometimes this is very straightforward, and we have a static corpus of data, like this email spam example that I've given you already. So there you just have a data set of emails, and your task for the AI is to figure out which of those emails are spam and which are not spam, right? But it doesn't have to be static data to be machine learning. For instance, if you think of your iRobot vacuum cleaner that you might have at home, right? This vacuum cleaner is also learning from data to improve its performance, right? It's using what is called reinforcement learning, which is another type of machine learning. So if you use the vacuum for the very first time, it's about the floor plan of your house or your apartment, and it will bump into a lot of things, right? But as it bumps into things, what it's really doing is it's collecting data of your environment. And if it's, at least if it's a smart robot, some of the more expensive ones, what it's doing is it's kind of iteratively build a map of your environment, and it understands more and more about its surrounding. It learns from data, and basically every time you use it, it'll become slightly more efficient at cleaning your living room, right? So this would also be machine learning. And again, deep learning as a concept is strictly within machine learning. So it's a type of algorithm that learns from data. So without yielding or telling you quite yet what deep learning is, you need to kind of see it within this sphere of machine learning. All right, but before we can dive into more details, we need to have a little bit of more appreciation and background of machine learning from a computer science perspective. One of the arguments that I often hear, and I'm not really taking any sides here, is that people, usually statisticians, when they hear about machine learning, they will tell you, well, you're just doing statistics, right? This is nothing new. Learning from data, what that means is you're just fitting a model to data, and then you do some sort of predictive statistics. Like, why should I even care about this as a separate field? And I'm going to try to give you an example that illustrates like differences between maybe classical statistics and machine learning with respect to the kind of problems we're solving. So let's assume this very practical problem right here. You have a bunch of patients, maybe those are inpatients at Nationwide Children's Hospital, and you have a bunch of data that you observe about those patients. You know the patient's age. Well, I guess these are too old. Maybe they're not at Nationwide Children's, maybe they're adults, but you know the patient's age, you know their gender, you know heart rate, oxygen saturation, temperature, I guess in Celsius in this case, some sort of variables, right? And you know an outcome about those patients. Those patients might be stable, those patients might be deteriorating. And now you're interested in the predictive modeling task of predicting whether a patient is stable or deteriorating based on this data, right? This is, in fact, this is something we're actually doing at Nationwide Children's Hospital. We have very similar algorithms in place. The textbook statistical thing to do here is to say, well, those columns in my table, those are potential variables, x1 to xk, right? And I can use these variables and I can plug them into a logistic regression model, because that's what we do. If we have data and we want to make a prediction, you use logistic regression. What you end up doing, without going into too much detail, is you're essentially pretending that the log odds of the probability of a patient being deteriorating, maybe I can make a laser pointer here. So the log odds of a patient deteriorating is really just a weighted sum of these variables that we have in our table. That's essentially what you're doing, right? And then you fit the model, you solve it for P, and you get a nice, interpretable, clean statistical model. And it's very nice, right? Because it tells you, for instance, that X1 is in the model, X1 is the patient age, it has a negative coefficient. So apparently, as the patient ages, the probability of deteriorating goes down. I don't know if this makes sense because I just made up this number, these numbers, but you know, this is what you get. It's nice, it's interpretable, you can do statistical tests, you can understand this model. The argument that I have that kind of differentiates machine learning from this kind of data set is that I would argue that you really only are interested in having an interpretable, nice, clean model because your data is clean and interpretable to begin with, right? The data is in a table and the data makes sense to you, right? You know what patient age is, you know that is a number and you know how to interpret that number. You know what the heart rate is, you know what temperature is, and you know what it means. So if you have a model that you can associate to these variables, it's a nice model that you can understand and that makes sense to you. For machine learning, this is usually not the case, right? In machine learning, the type of problems that computer scientists try to solve look a little different. So the kind of problem we have might be this. It's a person. The person says the word Alexa. So we have a sound wave somehow that represents data, and we want to build a predictive model that essentially does the same thing. It takes this data and computes the probability of that sound wave being the term Alexa or being not the term Alexa, right? So it's similar in the sense that we have a predictive model, but the data source is kind of very abstract. There's no variables here, right? There's just a sound wave, whatever that means. If you go back to the spam example, you have an email, right? You want to classify whether that email is spam or not. You need a predictive model. Well, what's an email? An email is fully just a bunch of source code of, your message and some header information, whatever it might be. It's a bunch of word jungle. Gmail needs to build a model that takes in that word garbage and somehow predicts whether it's spam or not spam, right? It's a predictive model, yes, but the data is kind of this complex, messy thing. Final example, let's say you have a chest X-ray. What is a digital chest X-ray? What is a digital image, right? Well, it's in the end, it's just a matrix of numbers, right? If we interpret these numbers as grayscale values, we can kind of look at them and it makes sense to us, but really to the computer, we just have a whole bunch of numbers. But somehow we want a supercomputer to ideally take in those numbers and tell us the probability that this chest X-ray has evidence of pneumonia or not, or something like that, right? So really what I'm trying to get at here, to put this into words, is that in the machine learning world, the data that you want to learn from could literally be anything, right? And given that the data is not easily quantifiable or even interpretable, like, why should we care about model interpretability? Like, historically, that didn't matter as much, right? And the way I like to think about this is that machine learning is more about like kind of pattern recognition than maybe explainability, right? We know we have this complex data source, like an image or whatever else it might be, or a sound wave. And we know the pattern is in there. The pattern that tells us whether the sound wave is Alexa or not Alexa, it's in there. We just need to find this pattern. What that really means, I don't know. I don't really care, right? The important part, why I emphasize this, is that maybe in comparison to like most statistics and statistical problems, the brain power, the human brain power in machine learning goes not as much into the modeling, but more into how to even represent the data, right? If we have a sound wave, what do I even have to do such that I can plug that sound wave into a statistical model, right? Because I cannot plug air into a model. What do I have to do to plug it in a model such that the model even has the chance to extract these important patterns, right? Whatever I end up doing, it needs to contain the important information, right? This is kind of historically where I think some of the differences are. In the end, do we use statistics and do we use statistical models? Of course, yes, why wouldn't we? But this is kind of why in the field of computer science, this kind of area has kind of developed separately and was coined machine learning. All right, so the process of extracting attributes from this raw data that we can then use to plug into a machine learning model is called feature engineering. That's kind of the term people use for that. So to give you an example, you have the sound wave. Sound wave is just a bunch of air. But what you can do with it, you can maybe do a Fourier transform or something like that. So you can represent that sound wave as some sort of frequency histogram or frequency spectrogram. That's still a lot of information. Well, but maybe all you need to know is how many frequencies occur how many times. So maybe you can just take a histogram of this spectrogram. And a histogram is something that's easier to quantify, right? A histogram is really just a bunch of numbers where each number tells you how many times the frequency exists in a bin, right? So without understanding the details about all of this, what I'm trying to tell you is that the idea is that we take the sound wave and we turn it into basically a vector of numbers. And a vector of numbers is a good thing because that's something we can plug into a model. We could even plug this into a logistic regression model if we so choose. Spam as another example. Traditionally, the way people treated this kind of problem is that they used what is called a bag of words, which means you completely ignore the structure of a sentence or anything like that. You just count the words that are in the email. And then you represent an email basically as a histogram of words, where you potentially could have every word in the English language in there. And you just count how many times each word appears in your email. That's again nice because again, you can represent that as a vector. You can take that vector of numbers, plug it into some sort of model, and you have your predictive machine learning model. All right. Yeah, that's just summarizes what I just said. So then, to make kind of the curve towards deep learning from traditional machine learning, you have to understand that kind of the traditional machine learning workflow that I was trying to describe you kind of always looks like this. You have some wild data source. You put a lot of brain power into hand designing some sort of features that you extract from this data source. That gives you some sort of number, some sort of vector. And then you plug that vector into a trainable model and get some sort of output, right? And that trainable model can be almost anything. I'm just dropping a bunch of words here. I'm not going over all of them, just you might recognize some of these. You might have read some of these in some context, but really all these are different mathematical models that allow you to analyze data in the shape of numbers and do either a classification of the data or a regression of the data. So all of these tools can help you do that, and kind of picking which one you choose is kind of part of the expertise of a machine learning expert. All right, so let's put this traditional workflow in context with what I will introduce as deep learning. This traditional workflow has one big caveat, and the caveat is that if you actually train your model to this data set, what you actually do is you do an optimization, right? A model usually has parameters, free parameters, and you're trying to basically fit those parameters to your data in order to make the model do something useful, right? In this traditional workflow, however, as you can see, is that because these features that you extract from the data are hand engineered, they're based on your expert knowledge, there's not really any optimization that happens here. It's just you have to rely on the features that you came up with. The only optimization happens between the output and the data in your features that you define. In other words, if your features are garbage, your model cannot possibly make up for it, right? There's no magic that can happen here. What would be nice is an alternative idea where you just take your raw data set, whatever it might be, and you plug it into one gigantic model that kind of takes care of everything. And that is called end-to-end training. You might have heard this term end-to-end before. It occurs a lot within the context of deep learning. And it's called end-to-end because there's just no manual feature extraction anymore, right? You just take your raw data, you plug it into this mysterious big model, and it kind of takes care of everything all the way to producing the desired output. The cool thing about this is that your optimization then goes across the entire spectrum here, right? You optimize directly based on your raw data, which means that as opposed to having to rely on whatever you hand-designed feature extraction you might come up with, you rely on the model to do this job for you and basically extract the right data for your task, for your need. And in practice, these kind of models that do this task are implemented with artificial neural network models. In fact, they are usually models with lots of layers. So they are what is called a deep neural network model. And effectively, that's why the whole thing is called deep learning, because you're using deep neural network models in order to do these tasks. And I will obviously talk about neural networks a bit more, but I've talked for a long time. So let me quickly summarize where we are already with this kind of first question that we were trying to answer. So we talked about classical statistical models. They require data to be available in the form of kind of clean numeric or categorical variables. However, digital data can take all kinds of forms. It could be sound, photos, images, text, whatever it might be. So machine learning then deals with the problem of how to transform these wild data sources into a shape that can be used to train predictive models. That's called feature engineering. And deep learning refers to machine learning models that can be directly applied to these wild data sources without a lot of manual effort in reshaping the data. All right. That's the first part of the lecture. Are there any questions at this point that I can talk about before I'll go into more detail? No questions? Are there questions in the chat window? I assume there aren't. All right, so I took a big sip of water and we can continue. So now that we hopefully understand kind of the context of machine learning and AI and where to put deep learning into this big picture, let's try to at least get a basic mathematical understanding of deep learning. To get a full understanding, you need to have a refresher course on like linear algebra and calculus, and it takes a while. I'm going to try to give you a 10-minute understanding of deep learning. So let's see how this goes. One thing I like to think about as kind of an introduction to this is a regression problem, because most people are familiar with linear regression, right? If you remember what regression is, essentially you have some data that's hopefully has some linear trend, and linear regression means that you're fitting a line through this data, right? That's what regression is. So you're already fitting a model to some data in the simplest form, right? The important thing is what you're actually doing by fitting this line is you're optimizing the slope of this line, right? The slope and I guess the offset define this line. So if this is just a one-dimensional data set where you only have a variable x, you're fitting the slope, which is the weight of your model, to this data, right? You can go from there to logistic regression pretty simply. Like logistic regression is kind of the same idea, which is why regression is still in the name. But all you do is you kind of squeeze your line into a logistic function. And what that practically does is it kind of turns your model from regressing a line to kind of finding a line that separates two types of data, for example, right? So that's essentially a way to think about logistic regression. And again, finding this model, optimizing this model is just finding the right weight, the right slope of this line. Now in computer science, we like to kind of reinvent the wheel and basically thought about this idea of logistic regression in the same way, but we called it a different, we just called it a different name. We called it a perceptron, but it's essentially the same idea. The cool thing about a perceptron is that you can think of it in terms of a network. Oftentimes in computer science, ideas are abstracted into graphs and networks that helps to think about a lot of things. So if you take this idea of a perceptron, you essentially do the same thing. You're trying to fit a line through some data, or it's in high dimensional data, it's not a line, it's some sort of plane, but think of it as a line. It's easier to think about it that way. So you have a bunch of input variables, maybe x1 to x4, and you're trying to basically predict a number. And what you do is you plug these numbers into this little graph, you sum them all up, multiplied by the weight, and then you threshold them, where the threshold might be telling you which side of the line you're on. So what happens is that the weights of this network define the slope of the line, and then the threshold tells you which side of the line you're on. So you're basically doing logistic regression, but you're doing this in terms of a network where you plug in the data on the left and the prediction comes out on the right. The cool thing about thinking of logistic regression in terms of a network is that once you have this idea, you can actually build a whole network out of little perceptrons. So you can take this idea of a perceptron, which is just doing logistic regression, and you build a whole network of these units that do logistic regression, essentially. That's one way to think about this. And the intuition that I'm trying to get at is that combining a lot of little logistic regression cells into one big model makes for a more powerful model, right? One way to think about this is that logistic regression is a linear model. It defines a line between two data points. If you can arbitrarily combine a lot of little logistic regression cells into a network, you can learn a lot of lines and combine them together and learn arbitrarily complex patterns in the data. So building a neural network is kind of a way at building a more powerful nonlinear model. Okay. That's intuition step one. For step two, let's think about a neural network in a bit more detail. But again, we're staying to a very high level here. So we start with a bunch of neurons. I call these circles neurons. And I call them neurons because they essentially just store numbers. One circle, one neuron stores exactly one number. And the idea is that the number represents the activation at that neuron. That's where the neural network idea comes from. It's supposed to be a network, so we are connecting those nodes with each other so they can kind of talk to each other. And then what happens is that in order to make this a model that can predict useful stuff, we kind of impose a direction. As you can see, I kind of put some arrows in here that goes from the left to the right. What we actually end up doing is we take some input, which could be any kind of data. So let's say those are 3 numbers. Those could be 3, I don't know, grayscale values of an image, or those could be 3 numbers that describe a patient, like patient age, temperature, whatever it might be. Those numbers then get propagated through this network with these arrows, and they form some sort of output. And the output is whatever number I would like to predict. So this could be 1 node with just a probability of the patient deteriorating. This could be multiple nodes because I want to maybe predict different classes of cancer. This could be whatever I want it to be. And the way this works is just real simple. The numbers go in here, and then they propagate from left to right. And at every node, you kind of compute a new number. And the new number is basically just the sum of all the nodes that go into this nodes. So here, those 3 yellow nodes go into this little black nodes, multiplied by the weight, which is given by this connection. And that's almost it. So you just sum up all these values, weighted by these arrows, plug it in here. The only thing you need to remember on top of that is there's this function g, which is usually called an activation function. These are just some examples about what people use for these activation functions. We don't need to think about this a lot. The important thing is, think of these as kind of threshold functions that they kind of define whether your neuron is activated or not activated based on the input to the neuron, right? That's really all you need to know. And the important thing is those functions are nonlinear, and we need nonlinearity in our model, because otherwise the whole thing just stays a simple linear model and we don't really get any power. But other than that, we don't need to think about it too much. But that's it, right? Data goes into your network from the left. You kind of propagate it through the network by multiplying it by its weights, summing it up all the way, and you get some output, and that's the output of your model. Easy. The question then becomes, how do we train these models, right? Because we want the output to not be any random garbage. We want the output to be the probability of a patient deteriorating, or whatever we might be interested in. So how does that work? How do we train these models? How do we fit them to data? So I made a simpler model here. This model only has 1 output. Let's assume that this output is supposed to be the probability of a patient deteriorating, right? 1 number between 0 and 1. And the input might be 3 numbers that describe the patient, maybe age, blood pressure, heart rate, who knows? Okay, I'm not a physician, I'm just making this up. So the idea is the following. You initialize these weights, the connections, right? It all depends on the weights of these connections, the weights of these links. You initialize them with completely random values, random garbage. And then what you do is you take an example of data, you take an example patients for which you already know whether that patient is deteriorating or not. This is important. This is why this is called supervised model training. So most deep learning models need to have labeled data in order to train them. Otherwise, you can't make it work. But let's assume we have a patient and we know whether that patient is deteriorating or not. We can then take the patient data, plug it into the model, and propagate these numbers with some random weights all the way through the output. And it'll generate some number. It'll probably be a garbage number because these are random weights, but it'll be some number. Let's say maybe the patient is actually deteriorating, so the actual output should be 100%. Maybe the garbage output is 0.3, whatever. What we can then do is we can compare the actual output of the model to the desired output of the model and compute how much it's different. We can, for instance, take like the square difference between the two, right? In general, what we call this function that compares the actual output with the desired output is called a loss function. Call it L here for loss function. The important thing is that this loss function depends on the desired output and the actual output. Well, the actual output is just dependent, it's just the functions of all your alpha values, of all these network weights, right? So really the loss function is a function of your network weights, which are the parameters of your model, and the desired output, which is what you want the model to predict. Well, that's nice, right? Because if we have something like this, we can go back and do some fancy calculus. We can take this loss function and basically take the derivative of the loss with respect to all these weights, and we would like to set that to 0, right? We would like to optimize these weights such that the output of this function becomes 0. Because if it's 0, then that means that the actual output and the desired output is the same, and our model learned something. Now, to gloss over a lot of detail, I'm just going to say there's unfortunately no straightforward way to optimize these things with like looking for global minimums or global maximums. What you do instead is you kind of approximate gradients or approximate the derivative with using gradient descent and essentially what is called a backpropagation algorithm, where you essentially iteratively push data through this network, look at the output, and depending on the direction of your gradient, you kind of decrease or increase those weights, and you just keep doing this and keep doing this until hopefully you have the right output. So that's the level that I'm comfortable sharing with you guys. And that's kind of a rough intuition about how you can train a deep neural network model. Now, obviously, the model I showed you is oversimplified, right? In practice, you have to think about these as being much more complex. Most state-of-the-art neural network models have tens of millions of free parameters. So they have tens of millions of connections between those neurons that you have to optimize. So you need a lot of data for this to scale, and you need to know what you're doing. Otherwise, this all just becomes garbage. Different building blocks turned out to have proven useful for different tasks. So it matters how you build your neural network. You can't just connect a bunch of neurons and hope for it to work. There's different tricks that people found out. There's, for instance, something what's called a convolutional neural network, where nodes are only connected sparsely to kind of neighboring nodes. This works very well if you have kind of spatial structure in your data, like for images. There's something called a recurrent neural network, where you have this recurrent loop. This can be useful if you have sequential data, like words in a sentence. You can have residual networks where you skip kind of neurons, which sometimes is useful if you have very large networks, because otherwise you run into optimization problems. You can have all kinds of things. What I'm trying to convey to you is that in reality, these networks are very large. And the real expertise, what kind of differentiates an expert in deep learning and a novice in deep learning, is that the expert knows how to best design the neural network architecture. So how to combine these neurons, how to build this network, and how to build the ideal loss function. So what function you're trying to optimize for your specific problem. If you're very good at designing network architectures and designing loss functions, you are probably an expert in deep learning and can make a lot of money right now. All right. That's the idea. A little bit of history on this. The idea of neural networks as statistical models is not new. It has been around since about the 1980s, I would say. So the idea that we can build a network, we can optimize it with backpropagation, like that's not really new. However, historically, these networks have received little practical attention. And the reason is that based on kind of small, simple data sets that we had in the 80s and then the 90s and even in the early 2000s, these models don't really outperform much simpler models like logistic regression or some decision tree on most small data sets. So people thought about, why should I care about this complicated neural network model if I can just do logistic regression and I get the same output, right? But things kind of started to change around 10 years ago, right? And this is largely driven by a couple of things. One is the availability of large labeled data set at a larger scale. So to give you an example, I did my PhD in computer vision, so I did machine learning for images. And 20 years ago, the best data set that you could find was like Caltech 101. It gives you like 100 images of cats and 100 images of dogs. And there you go. Now try to differentiate cats and dogs, right? What we now have are like data sets. And really this is because, collecting this data is easy because of the internet. Even annotating this data is easy because of the internet. We now have millions of images. There's a data set called images. It contains, I think, 5 million images of 1,000 different object types, and they are all annotated. So the scale is just immensely different to compare to what it was maybe 10 years ago. In addition, an important factor is computing hardware. So these models, again, are huge. They have lots of parameters. You cannot just optimize a deep learning model on your laptop. You need better hardware. You need GPUs usually, which are processors that are optimized for this kind of math, for this kind of optimization. And these have become more and more affordable to people over the last 10 years. And then lastly, what I like to point out is this paper, which is my favorite paper, Image Classification with Deep Convolutional Neural Networks. This paper is historically important. It's from 2012, because it was kind of the first paper that kind of proved that you can take neural networks, scale them up drastically to large data sets, make it actually work from an engineering point of view, and basically get a much higher performance than any non-deep learning model on certain tasks like image classification. So this kind of 2012 paper by George Hinton, was a very big name in deep learning. You may have heard of him or read some articles about him. Basically made everybody switch to deep learning for the next 8 years. And just to measure this impact, I pulled this screenshot, I think 3 days ago. This is a paper from 2012. It's been cited 72,000 times. That's right, that's 72,000 times. Now, citations in computer science are a little bit inflated compared to other sciences, but trust me, 72,000 times, that's quite an impact. All right. So again, to summarize this part, deep learning refers to machine learning based on deep neural network models with many layers of neurons. A neuron essentially just stores a single number. That number is the weighted sum of all of its input neurons plugged into some sort of nonlinear activation function. Training a model means updating the weights of the connections between neurons until the desired output is achieved. Different building blocks work well for different purposes, and really knowing how to build your network and how to define your loss function, that's where the real expertise lies. And a well-designed network, and that's important, can learn to transform the input data, i.e. build features and make predictions at the same time. However, because models have so many free parameters, they need a lot of training data, usually in the order of millions of samples, in order to be really useful and really powerful. Any questions at this point while I take another sip of water?
Sven, I've got a question. There's
yes,
kind of heuristics in traditional statistics that we learn to use, and I think a lot of our physicians have probably learned to use. If you see something like logistic regression, you look for independent observations and these kind of ways to get a pulse on whether or not the model or the methodology is trustworthy. Is there like any quick litmus test that you'll look at when you see a paper using deep learning in medicine, that you can just rule out, I think this paper is overhyped out of the gate? There might not be. Is there anything you look for?
Right. Yes. I mean, so one aspect that I don't really have the time to cover here is, these models, because they are this huge, they're kind of, they're intrinsically black box models. So you don't know right away what's going on or what they're even learning. Now, that's not entirely true, because obviously people are doing research in better understanding these models. And there are some tricks that you can do. For instance, in computer vision, you can visualize areas of an image that the model used to make a decision, things like that, to try to understand it. But it's still somewhat of a black box model. So you need to just swallow that pill if you want to use deep learning. But to answer your questions, what I do with papers to see if they're garbage or not is just I look at kind of how the model is trained and evaluated, whether that was done properly. So do you have enough training data to even make this worth it? And are you not overfitting your model? Because one problem with deep learning is because you are not defining the features, the model is defining the features. The model will learn to use any pattern in your data that it can use to make the right prediction. Now that pattern might be what you want to predict, or that pattern might be some random bias that you're not even aware of, right? And there's no straightforward way at finding this out. So you need to be very careful about designing your data sets and properly validating your models. like for example, in a lot of like radiology use cases, we have the problem that we don't have that many CT scans. We usually don't have access to millions of them, right? So people try to use small CT scans as data sets, and they're not thinking about how to pre-process them. And they think their model works well, but what actually is happening is that maybe all their CT scans that contain cancer have some sort of weird bias. Maybe they have some little marker on the bottom left where somebody annotated something, or maybe they have, I don't know, a slightly different grayscale value. I have no idea, but any kind of bias that you have in your data set, the model will detect and take advantage of. So it's kind of up to you to make sure that your model learns what you want it to learn and not just learns any kind of bias. Very long answer. I hope I at least partially answered your question.
Yeah, you did. Thanks. Sorry, that was kind of I was thinking about it the whole time you were talking because it's not something I've asked you. So I appreciate it. Thanks.
Sure. All right. So before we run out of time, let's try to get an understanding about where deep learning can actually be useful and where it maybe not be useful. Because, you know, I've talked a lot about it, and you might think, so is deep learning now the solution for everything? Should I use deep learning no matter what my problem is? And the answer is absolutely no. It's not the solution for everything. This is kind of my personal kind of taste here, but I think domains in which deep learning have proven to have significantly improved the state of the art are kind of three types of domains. One is images and videos. So basically anything where your data has spatial structure, and spatial structure is important, or maybe temporal structure is important. Sound and audio, like automatic speech recognition, usually for the same reasons. There's spatial structure or temporal structure that's important. Or text and language. So this means natural language processing, machine translation, and these types of problems. And I would argue that any modern AI algorithm that people show you that requires analyzing images, sound, or text is very likely to use some type of deep learning. So I think these are the areas where we know that deep learning works very well. And I don't have the time to explain for each of those domains exactly how deep learning works, but I'm trying to give you an intuition in the next couple of slides as to why deep learning is beneficial for these types of data sources. So let's start with images. So you just kind of have to believe me that an image is an incredibly complex data source. Just think about it real quick, right? An image usually has millions of pixels. Even a tiny image doesn't have to be that big of a resolution to already have a million of pixels, right? Each pixel can potentially have tens of millions of colors, right? So there's just an incredible variety of things that can be captured at an image, right? It's a very complex data source. And as it turns out, and we have like 30 years of computer vision research to prove this, even the most complicated hand-designed features that very smart people thought of, they just don't work very well. You can come up with the best hand-designed feature, and really it cannot even robustly detect the dog in a picture because it's just so hard of a problem. However, with deep learning, you can kind of take advantage of the fact that if you have enough labeled images, let's say you have 1 million images labeled as cats and you have 1 million images labeled as dogs, and you train a neural network, and I call this a CNN here, it's called convolutional neural network, specific type of neural network. You train it long enough and you build your network right. What the network actually does, it can learn thousands of filters that can extract increasingly complex patterns from the image. And again, I have no time to go into detail, but the intuition here is that if you're really smart about how to build your network, you can make it such that optimizing the weights of your neural connections basically becomes the same as optimizing filters that go through your data. That's a matter of building a network with the right architecture. So by optimizing a neural network, you're optimizing network weights. What you're actually doing is you're finding filters from scratch. And because you have a labeled data set, you can keep playing this game such that eventually your model will find filters that can figure out whether your picture contains a flower or a cup or a car. If you're interested in this topic, computer vision is actually my all-time favorite topic. I'm very happy to go into a deep dive here. I can give you an entire lecture about how a computer learns to analyze a CT image. So just let us know in the feedback. We can make a lecture about this. But for now, this is kind of the depth that I can go into. What I do want you to know, though, another reason why this is so successful is that you can build these neural networks to essentially produce any kind of output you want. So you don't have to leave it as plugging a picture into this model, and then the model tells you, yes, there's a cat. If you design your network in a smart way, and if you design your loss function in a smart way, it can spit out almost everything. So you can use a neural network to just, for instance, detect a cat and also give you the bounding box of the cat. You can give bounding boxes of even multiple objects in an image. You can even do segmentation right away, where the model directly finds the cat and basically highlights the pixels for you. This is obviously super important in radiology, for instance, when you want to segment a tumor, for example, right? But it doesn't even have to be a class of something. You can even combine neural network models for vision with neural network models for speech, which I'll talk about in a minute. And you can build a neural network model that takes an image and produces a sentence description of that image, like a caption of that image. All that is possible. You might have seen style transfer applications. I think there's an app, what is it called? Can't think of the name. Prism or Prisma, something like that. there's a famous phone app where you can basically take a picture and you can make it look like a Van Gogh painting, for example. That's using deep learning, right? So you can plug in the picture, you can plug in a Van Gogh painting, it'll produce some sort of mixture. You can take it all the way to extremes. You might have heard about deep fakes. So deep fakes are also neural network models that they're actually using GANs, what are called generative adversarial networks. And they can produce entirely synthetic images that don't exist in the real world. Like you've probably seen examples like this, where you take Amy Adams and turn her into, I think this is Nicolas Cage, because of course it is Nicolas Cage. we're on the internet. But you've probably seen these examples. I don't need to tell you the dangers that come with these kind of manipulations of data, but this is all using the power of deep learning. So that's images. Why does deep learning work well with sound? Like, why can we say, Alexa, what time is it? And the model, Alexa knows the words based on sound waves. Why can we do that? There's actually a trick that makes this work, which is you turn the sound and just turn it into spatial data, and then you use the same CNN that you use with images, and it works quite well. So again, if you have a sound wave, I told you earlier already, you can, for instance, express that sound wave as a spectrogram of frequencies. And really the spectrogram is just a picture, right? This is an image. This image contains patterns. These patterns are important. So I can use a convolutional neural network that might take this image and classify what phonemes are in this picture. Phonemes being like the building block sounds of language, like p, b, t, those are phonemes. And while you're at that, and you know the phonemes, you can plug that into a language model, maybe a recurrent neural network, and that will then tell you, based on the phonemes, what's the most likely sequence of words, right? And because it's deep learning, you can do this whole thing end to end. You can do this whole optimization with one big neural network. All you need is kind of annotated data. Now this is kind of voice recognition. So this is the task of turning sound into words. Words are still just symbols. We don't really understand what those words means at this point. In order to understand what words actually mean, that's a task called natural language processing, and deep learning works very well here as well. I'm running a bit out of time, so I'm going to speed this up a little bit. The important thing you need to understand is, in order to do this, we need to represent words as numbers, because we need numbers to do our math. Traditionally, there was not a very easy way to represent words of numbers that are semantically meaningful. So there might be, you might be able to encode every word in the English language into some vector of numbers, but those numbers don't really have any meaning. The number, the vector for abbreviation might look similar to the vector for A, but those words have nothing to do with each other. With deep learning, what you can do is you can actually learn what is called a distributed word representation. And that's important because it gives you a vector that actually carries semantic meaning. Again, I will not go into details here, but you can trust me that you can build a big neural network in a clever architecture, and what you will get is some intermittent layer of the neural network which represents words as numbers, and the numbers have meaning. And you can prove that by kind of doing math with those numbers. And this is called a vector representation of those numbers. And you can see, for instance, that the vector of king relates to the vector of queen in the same way a vector of man relates to the vector of woman, and all these kind of things. So you can show in a fun way that deep learning can represent words as numbers that are semantically meaningful. And just like with CNNs, you can use these models. They're usually called transformer networks for natural language processing, and you can produce all kinds of outputs and use this idea for various tasks, like your voice assistants that interpret the command that you tell Alexa are using deep learning. Machine translation, if you go to Google Translate, you translate a sentence from German to English, it's using deep learning. Chatbots that you might talk with at some site when you're trying to get tech support or something, that is using deep learning. Auto-completion, text suggestions, if you write a Gmail email and it tells you how you should end your sentence, that is using deep learning. There's even things like text summarization and question answering. So you have a large text and these models can try to kind of summarize the gist of it. All right. So this is kind of giving you an idea, or the reason I talked about these three areas, you know, images, speech, and natural language processing, or sound and natural language processing, is to give you an idea about where this stuff works. Now, if you want to tie this back to medicine, you know, you can kind of directly see some of these applications that are helping people already, right? This kind of idea of pattern recognition with structural data obviously helps with medical images, right? So deep learning is all over the place and trying to find patterns in CT scans or in MR scans, whatever it might be. But it also works with EKGs, for instance. There are papers that take an EKG reading, which is just a temporal signal over time, which has structure. And if you have enough data, you can have a deep learning model that kind of can even classify or detect different arrhythmias in the EKG automatically. So it's already there, right? Natural language processing, those deep learning technologies are also already there. If you're taking patient notes, some of you might be using like an app where you can just talk to instead of having to write it all on your own. This is using deep learning. For a lot of our analytical projects that we are working on as a data science team, where we are interested in data from the electronic health records, we often use natural language processing that is using deep learning in order to interpret the free text medical notes that physicians write into the health record, right? Some of the health record data is structured, and that's easy, like a CT code, not CT code, what are those codes? ICD code. That's easy to understand for a machine, but a medical note that you just write is not easy to understand. So we need to use natural language processing in order to make sense of that data. This is kind of cases where deep learning already works. The kind of magnum opus that kind of Google and all those big tech companies are trying to do to kind of change medicine, or whatever they might call it, is trying to find what they think a deep embedding for a patient based on the electronic health record. So the idea is that if you can use deep learning, for instance, to find a complicated vector that captures the meaning of a sentence, you can also use deep learning to basically summarize all of the data that are in the health record of a single patient into a deep embedding, and then use that embedding to predict anything you might be interested in. So the insurance company might be interested in future healthcare costs. The hospital might be interested in, you know, the probability of an unplanned readmission. The physician might be interested in potential future diagnoses, all these kind of things. In practice, however, this is an area where deep learning has not really taken over yet, right? We've not been entirely replaced by AI, simply because these kind of data sources are very complex and very kind of messy, and it's not as easy as kind of plugging an image into a neural network. So that people are working on this, but deep learning has not yet taken over this field because it's not the solution for everything. final slide. I know I'm about 1 minute over. I apologize for that. Is deep learning right for me? If you really want to know, just reach out to us. If you have any kind of project and you're trying to figure out, do I need deep learning here? Do I need machine learning? Do I just want a statistician? Reach out to us. We're happy to help you. A couple of rule of thumbs that you can go by with that I wanted to close with is that deep learning may help you if you have a data set that is large, whatever large might be. Ideally, that data set is already annotated, because you remember you need to have annotated data in order to train these models. And ideally, your data set has some sort of spatial or sequential structures. So if you have time signals, text, images, that's great. We can probably use deep learning. Deep learning may not be very helpful to you if your data set is small, whatever that means. If your data set is tabular, so you just have a bunch of variables, like this patient iteration example that I gave you, or when it's very costly to annotate your data. All right, that's the summary. That's my last slide. Sorry for going over by 2 minutes. Thank you for your attention. And if you have questions, I'll be around for the next couple of minutes. Thank you very much.